Okay, so in part one, we started taking a look at the situation involved when we want to do a binomial probability question. Like, for example, I started out by talking about, let's imagine we had a fair coin and we were going to flip it 3 times and so on. And I can write out the whole sample space. You'll remember that I did that. And we can take a look at the sample space and analyze the question based on that. But now we're talking about, and there's other brute force methods to do this, like a tree diagram. But now we have a harder question. In 10 flips of a coin, what's the probability that we'd get exactly 3 heads? And that's much harder. There's no way to do, in practical terms, a brute force method to help us answer that. I mean, if I did a tree diagram that showed us 10 flips, it would be like ridiculous. It would have over 1,000 branches. By the way, if you're curious about how I came up with that number, send me a message and I'll answer you, or maybe I'll do a little mini video. Anyway, massive number of branches in a tree diagram that would demonstrate to us all the different ways 10 flips of a coin could come out. And by the way, it's not important now. We're going to need to worry about it later, but not now. But just to recall the whole situation, we were imagining that we have a coin where the probability of heads was 2/3 and the probability of heads complement was 1/3. So that's the scenario. But anyway, so we have 10 flips and we want to calculate the probability of exactly 3 heads in 10 flips. So how are we going to do that? Well, the first element, which we talked about in part one, was the fact that now the coin is independent. Each flip is independent. So we're going to end up multiplying the probability of heads 3 times. Probability of heads times the probability of heads times the probability of heads times the probability of tails in a sequence 7 long to give us all of our 10 coin flip outcomes and so on until we have the 10th outcome. So we might imagine that we have heads, 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 and then tails, tails, and so on through to the 10th trial. And that's all well and good, except that if we just multiply that out, we're not going to have the answer. There's an extra element here. And the extra element comes from the fact that we might distribute those 3 heads through our sequence of 10 flips any old which way. We have to account for a situation where we might get heads, 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 tails through to the 10th flip. How about this? Heads, tails, tails, heads, tails, heads. I'm just being random now, all the way through to the 10th flip, and so on. We'd have to imagine every one of those scenarios, and we'd multiply the probability of heads to the 3rd power, multiplying the probability of tails to the 7th power. We'd have to multiply that by how many different ways we can get the sequence of 3 heads and 7 tails. I hope that makes sense. So what we're going to do, and this is more or less a rehash of the last video, what we're going to do is we're going to use combinatorics or counting problem methods and procedures to help us with this part of the problem. So the topic is combinatorics. And we're going to use a subtopic of combinatorics called combinations. Now, how does this work? We are going to utilize this math to answer the question, in how many different ways can we choose 3 locations within our sequence of 10 trials to sort of house our heads? So I have how many there? That's 7, 8, 9, 10. So we have 10, let's call them seats or potential locations for our 3 heads to settle in. And all the rest will be tails. We could have heads here and heads here and heads here, or heads here and here and here, and so on. You get the idea of that randomness. We're going to use a formula called the combinations formula, and it looks like this. It is n exclamation point okay, so n exclamation point over r exclamation point n minus r exclamation point. So what's the idea behind those exclamation points? Okay, nobody's angry. We didn't have too much coffee. It's there for a reason. It's actually a math direction. When you have n exclamation point, it means n factorial. It means to do this. You're going to take n and multiply it by n minus 1, and then multiply n minus 2, all the way down the road until you get down to 1. And that product, the result of all that multiplication, is n factorial. So what we have in the formula for combinatorics right there is how many different ways can we choose r spots from within a sequence of n potential spots. That's how we can think of it and apply it in this problem. We write n c, big C, r. Another way to write it would be big C, n, comma, r. That's another way to write it. Another way to write it would be n floating above an r in a big thing that looks like a parentheses. You almost want to put a fraction line in between, but you really can't. You shouldn't, because that would be incorrect. Those are all different ways of writing n choose r. That's the way it's expressed. Let me make some room for myself right here. I'm going to rewrite the formula. So let's take a look at how we would do this. We're going to do that like this. Let's say we want, and I'll use a smaller example. Let's say we want 5 choose 4. So I want to know, out of 5 potential spots, how many different ways might I arrive at selecting 4 of the spots to house my heads, for example. And by the way, don't forget that in binomial probability, it's really more customary to talk about success and failure than it is to talk about heads and tails, but I'm just talking about heads and tails here to keep it simple. So I'm going to have 5 choose 4. So I would write 5 factorial over 4 factorial, 5 minus 4 factorial, as I showed you in the formula before. 5 minus 4 is 1. That's going to look like this. That's going to be 5 times 4 times 3 times 2 times 1 over 4 factorial, that's that, times 3 times 2 times 1 times 1 factorial, which is just 1. Okay. So this is a fairly easy problem to do. I want you to notice that we have 4 factorial as a component of 5 factorial. So the 4 factorial on the bottom cancels with the 4 factorial component of 5 factorial. So that goes away, and we just have 5. And that's the answer. Let's do another one. Why don't we do, let's do 6 choose 2. So now we're going to have a sequence of, if you want to think about this in this way and keep it grounded. Let's imagine 6 coin flips, and we're doing part of a binomial probability calculation where we're trying to figure out how many ways can we have 2 heads, 2 successes from among the 6 trials, the 6 coin flips. So we're going to have 6 choose 2. Here's another example. I'm still utilizing the formula. Let me write a general version of the formula right here, just so it's on screen with us while I'm doing it. I think that might be helpful. 6 choose 2, let's do that. That's going to be 6 factorial over 2 factorial and 6 minus 2 factorial. I didn't go straight to writing 4 right there. Now my students know I think it's kind of a really useful thing to do this by hand. If you can do this by hand, you know, you're going to be a tougher and more aggressive mathematician. That's always a good thing. And you're going to see inside of the problem and learn the math a little bit better. Really a good idea. You don't have to. Scientific calculators, graphing calculators, and I think most phones, I gotta say probably all smartphones, will either have an ability to do combinatorics or you can download an app or something. But a lot of times you'll find that with a little practice, you're going to be faster doing it by hand than somebody else will while they do it on a device. Look at what I wrote here. Instead of writing 6 factorial or 6 times 5 times 4 times 3 times 2 times 1, I went straight to representing the tail end of that 6 factorial as 4 factorial, because that's what it is. 6 times 5 times 4 times 3 times 2 times 1. Over here on the left, I've just carried the 2 factorial over. That's going to be 2 times 1. And then I'm multiplying it by 4 factorial because, and this would go a lot faster if I wasn't jabbering while we're doing this, but those 4 factorials go away immediately. So we have 6 times 5 over 2 factorial, and that's just 3 times 5. Do you see why? Over 1 or 15. So 6 choose 2 is going to be 15. Let me make some space. I'm going to write out some practice questions, and I'm going to leave them for you for a moment. I'm going to ask you to pause the video, and then I'm going to go ahead and solve them with you, okay? Okay, guys. I used a little video editing to make the problems pop up right away. So that's I think a good start for us. Let's take a look at this. The first problem would be 7 choose 3, as if we had 7 flips and 3 were heads, 3 were successes. Remember, at some point, if you're going to study this, I would really think it would be a good idea to get ready to extend this more broadly. But right now we can keep it rooted in our problem with the coin. 7 choose 4 is the next one, and then finally our problem as it pertains to the problem that I set out for us at the beginning of part 1, 10 choose 3. So please go ahead and pause the video. Do please to try to work all 3 of these, and then we're going to work them together. Okay guys, I'm going to assume we're back. If you didn't have enough time, pause the video now. If you're back with me, good. Let's go ahead and do it. I'm going to make some space. And we are going to do this without the combinatorics function inside a device. By the way, Excel has that too. The first one was 7, what did I say? 7 choose 3. So 7 choose 3. Let's go ahead and do that, okay? We're going to have 7 factorial over 3 factorial and 7 minus 3 factorial. So 7 factorial is actually, we know that that's 4. So we know that 7 factorial is 7 times 6 times 5 times 4 factorial. And that's above 3 factorial times 4 factorial. I'm going to set it all the way over here so it's really just obvious in our face that right off the bat we can cancel that. So now we're looking at 7 times 6 times 5 over 3 factorial, which is 3 times 2, times a redundant 1 if you want to put it in there. Well, 3 times 2 is 6, so I can cancel the 3 times 2 against the 6 on the top, and I get 7 times 5, which is 35. So that would be the answer to the first one. Let's go ahead and do the next one. And if you did it and got the correct answer, you saw that I was trying to make a point with this. Here's the point. Okay, 7 choose 4 is going to be, I'll get to the point at the end. 7 factorial over 4 factorial, 7 minus 4 factorial. And that is, of course, 7 times 6 times 5. Now I'm going to follow the same pattern that I did the first time. 7 minus 4 is 3. So I have 7 times 6 times 5 times 4 times 3 factorial this time on the top. And we have 4 factorial on the bottom times 3 factorial. Those go away. And what are we left with? 7 times 6 times 5 times 4 over 4 factorial. 4 times 3 times 2 times a redundant 1 if you like. Well, look where we are. The 3 times 2 still cancels versus that 6, and we have a 4 canceling this 4, and again we're left with 7 times 5, which is 35. So we're still in the same spot. Comes out to be the same. That is a rule. The rule is this. N choose R is equal to N choose N minus R. Like in those two problems, for example, it doesn't really matter if we say, let's choose 3 spots within 7 to use. It's really the same as, let's choose 4 spots within 7 to not use. It's a difference in phrasing, but it means exactly the same thing. So 7 choose 3 is the same as 7 choose 4. Okay, because that is 7 minus 3. We can look at it both ways. So those ought to be equal, and that has the potential to maybe make things easier for you at some point, right? You can realize if you have a big problem, 100 choose 99, the math would look like it would be horrendous, but it's really just 100 choose 1, isn't it? It's going to be the same. Anyway, let's do that third problem, the problem that pertains to our main overall problem that we're doing through these binomial probability videos. And then I'll follow up with some basic like shortcut rules right at the end. So we had 10 choose 3. And that's going to be 10 factorial over 3 factorial, 10 minus 3 factorial. And that's going to be 10 times 9 times 8 times 7 factorial. We know exactly what that is. We're going to put that above 3 factorial times 7 factorial. Okay, I'm canceling right away. And so we have 10 times 9 times 8 over 3 factorial, which is 3 times 2. Now, we don't have total cancellation possible from the denominator to the numerator, but we can do some things. For example, 3 cancels with one of the factors of 9, and 2 cancels with part of the 8, because 8 is just 2 times 4. So I'm left with 10 times 3 times 4. And a little thought will tell you that's 10 times 12, which is 120. Okay, so we need that. In part 3 of this video, we're going to put this all together. We're going to put together the probabilities of failure and success, that is, the probability of heads and tails that we got from part 1. And we're going to multiply it by the correct combinatoric expression to get the actual answer to the question that we asked. Before you go, and before I go, let me give you some basic rules for combinatorics. In general, n choose 0 is 1. That makes sense because we're asking, actually, let me put that in the format that I've been using. N choose 0. That makes sense because we're asking how many different ways are there for us to choose 0 spots from within a sequence of n spots, and there is only one way not to choose any. Here's another rule. N choose 1 is n. Let's see. N choose n is 1 also. And those go together, don't they, based on what we were just talking about a few moments ago. N choose n minus 1 is also n. You can prove that. Send me a message if you want me to show how to prove that is true. It's actually kind of a cool, and it's elegant, and it's quick, and it's something interesting. We can prove that that's the case. One more thing, by the way. As you're doing this, you may not need it particularly for this exercise that we're doing right now, but just because I ought not to leave it out, 0 factorial is, I'm tempted to say by agreement, but there's an actual reason for it. 0 factorial is 1. So 1 factorial is 1, 0 factorial is 1, which sounds odd, but it is the case. Okay, guys, so go ahead, see if you can answer the question that was posed during part 1 of this series on your own. Let's make that our cliffhanger this time. Given that you're going to flip a coin 10 times, what is the probability that you'd get exactly 3 heads in 10 flips, given that the coin has a probability of heads of 2/3 and a probability of tails of 1/3? I think you have all the components to be able to answer that question now. So go ahead and try that, and we're going to do it all together in part 3. Thanks a lot.